Hello again. This is the second video on chapter 3. So last time I left off one problem and I'm going to do it this time, and we're going to continue with chapter 3. Okay, so let's get started. I hope you're doing well. So we are going to talk about this problem that last time we didn't do. So the reason I want to do this problem, it's a good example of application of calculus. So here is an example where we want to build a company wants to design a track for a toy car, and the toy car has to basically be able to come down smoothly on this track. Now, here is the formula for the track, and notice that is a piecewise function, and part of it is a curve, and part of it is a straight line. The point of connection here that connects the two paths has to be such that basically the car would go right on it smoothly. So that's the idea of a curve being smooth or having a sharp corner like that. See? So if it's the connection between the curve part of the path and the straight part of it, if it's not smooth, then the car would not ride on it smoothly. So the point is that we have to find B and C here, so such that the connection between these two would be smooth. So in order to be smooth at that point, right, then it has to be continuous first of all. So you don't want it to look like this. And it has to be smooth. That means you don't want it to look like you have a curve and then a straight line like that. So there's a sharp corner there. So in order for that to be true, we have to find B and C such that this function is continuous at -10 and differentiable at -10. So in order for the f of x to be continuous at -10, we know the definition is that the limit of f of x when x approaches -10 has to be the same as f at -10. That's the definition of continuity, right? So let's set it up like that. So we take the limit from the left, which means we have to take this part. That's the limit from the left. And we substitute -10 for x. And we end up with basically this. So that is the limit. This is the limit from the left, right? Now, limit of the function from the right, we have to use this one. And we use it and then substitute -10 here. We get that, which is 5. So limit from the right is 5, right? So what we have to do is we have to make sure these two are the same, and they're the same as f at -10, which is actually 5. So we're going to set this equal to each other, this one and this one. And since we have two unknowns here, we're not going to be able to find C and B, but we find a relationship between what? Between B and C right here. So that's the first step. Okay, now, so that was the continuity requirement. What about the differentiability requirement? Well, for this function to be differentiable, this limit has to exist. Remember the definition of derivative at a point? So f prime at -10 has to exist. So we set up this limit again from the left and from the right. So from the left, again, we have to use this part of the function, right? Remember? So it would be f of x minus f of -10. So that would be f of x. And minus f of -10, we know is 5, right? So that's minus 5. Denominator is just x minus -10, which is x plus 10. And here now we have to find the limit, so we have to take what? negative 10 and substitute for x here, negative 10, right? And we end up with, we are going to, let's simplify it first. So in order to, now we can't substitute for negative 10 here because, again, you know this is derivative and there is trouble built into it, and that trouble is 0 over 0. So we can't just substitute and get it. So we have to basically try to factor the numerator and get x plus 10 out of it. How? Well, it requires a little bit of algebra, because we have a quadratic that has what? That has b and c of the quadratic. You know, quadratic looks like ax squared plus bx plus c, right? If we want to factor this, right, we can think of it as, find the roots of it and factor it. We can think of it as negative b plus and minus the square root of b squared minus 4ac over 2a, right? So in this problem, this b right here is actually what? Is this b right? Let me look at this more simplified form right here. So that would be our b, which is the coefficient of x, and our c is this whole thing. So we have a quadratic we want to factor, right, in the numerator, and this is the b and this is the c. So we put in the formula right here. This is not a fraction, that's just a formula, and then we put what b is, which is 10 positive 10b, that's our b. So if you square it, we get 100b squared minus 4 times a times c. Our a is 1, right? And our c is this thing, so we put it there. And we end up with this right here. So x equals to that. It gives us two answers here, right? So we're going to substitute here with the plus and with the minus. So with the plus, we get negative 10. With the minus, we end up with negative 10b plus 10, right? So we got this, and we got this right here, right? So there are two factors. So now we can factor the numerator. So let's do that. So here we go. So one of them was, let me go back to show you. So one of them was negative 10 and one of them was negative 10b plus 10, right? So it would be x minus negative 10 and x minus negative 10b plus 10. Those are the two factors. And right away, we know this cancels that. So we end up with 10 in the denominator. We can bring it out, write it as 1/10. And then limit of this when x approaches negative 10, we could use with substitution, right? We can just do substitution, simplify the substitution. We get what? We get b minus 2, right? So that is the left limit for the derivative. Now the left limit equals to that. Now we take the right limit, which is much easier, because for the right limit we have to use the linear part of it. And we simplify, we get negative 1/4. So what does that mean? That means this has to equal to that for this limit to exist, right? So we set it equal to each other and we find b. And remember, we had a connection relationship between c and b, so we can find c here too. So c should be 25 over 2 and b should be 7 over 4 in that piecewise function. So that's what it is. Now, I'm going to take you to a animation of this quickly. So remember, c has to be 25 over 2 and b has to be 7 over 4. So we are going to let's see. So what I'm gonna, here, you see this path? That's the same problem. I created this with the different b's and c's. And you see what happens if you change b and c's. there is a point where this thing has the shape that we want and is going to work, right? So we're going to change, we want C to be what? Let's see. What do we want it to be? We want B to be 7/4 and C to be 25/2. So 25/2 is like 12.5 something. Can't get it. But let me, this is online one, doesn't want to cooperate. So I'm going to get the one that I have in my computer. So let me go do that quickly. Calculus 1. Here you go. GeoGebra and the toy card right here. So I'm going to use that right here. All right. So as you see, I can change that. You see, when is 12.5 right there, and B is what? B should be 7/4, right? So let me put right here. So I'm going to make B be 7/4, and C is 12.5, and you see it's connected and it's smooth and continuous, right? Otherwise, you see, any other B and C would not work and would change this. So either it wouldn't be smooth or wouldn't be continuous, right? All right, so let me go back to what we were doing. All right, so here is an example of application of calculus where this is actually matters when you want to build this path, right? You have to take that into account, otherwise it wouldn't be working. And also was a little bit of algebra involved, so it's a good problem overall. All right, so let's continue and talk about higher order derivatives. Higher order derivatives means taking more derivatives, right? So once we take a derivative, we can actually take another derivative, right? So for example, if f of x equals to x to the third, then derivative of it would be 3x squared, and then derivative of derivative would be 6x, and so forth. So we can keep taking derivatives. Now, derivative of, we're going to talk about this in the next section, but derivative of x to the nth power, the derivative of that is nx to n minus 1. And that's the formula we're going to prove in the next section. But for now, that's what it is. So derivative of x to the third is 3x squared. Derivative of 3x squared is 6x. And derivative of 6x is 6. And derivative of 6 is 0. We're going to talk about all that. But for now, that's what we mean by higher derivatives. So the notation we use for higher derivatives are similar to the notation for first derivative, except with this notation, we cannot go more than 3 of these things because it becomes just ridiculous to put a bunch of these little primes, right? So up to third prime, you see something like that, but otherwise you will see something like this. So when you do f and then you put parentheses, some number in there, this notation is for derivative. So that means first derivative. We can either put zero derivative here. Zero derivative means the function itself. That means don't take derivative. And with y double prime and y prime, y prime, y double prime, y triple prime, again, we use numbers if we want to do higher derivatives. With the Leibniz notation, this is what we do. So dy dx is the first derivative. And think of like we want to take another derivative of this. So d of d, we write it as d squared. And then dx times dx, we write it as dx squared. Okay, that's how we write it. And then the third derivative, fourth derivative, and so forth. So remember, we don't put the 2 over here. we put it over the d in the numerator. In the denominator, we put it over the x. And so that's what that is. And so the position of a particle along the coordinate axis at time t is given by this. Find a function that describes its acceleration at time t. Okay, now, if we have the position function, the derivative of position function is the velocity. And the derivative of the velocity is acceleration. So acceleration is the derivative of the velocity, which is double derivative of the position, right? Because to take derivative of this, that means you're taking another derivative of position function. So that's the idea of connection between position, velocity, and acceleration. So S prime here, we still don't know the formulas to take S prime, so we have to use the limit idea. And you can stop the video and look at this limit. You see you get 60 minus 4. I don't want to redo this again, but redo this. So this is the first, so that's the velocity. Now we want acceleration, so we're going to take another derivative. That means this time we're going to use this, right? This is velocity now. So we're going to take the prime of that. And to take the prime of that, we have to take the limit again, but this time this is our what? The function that we're going to use, right? So we're going to use the S prime here as a function, right? And that limit is 6. So acceleration for this is 6. That means there's a constant acceleration involved in this movement, whatever it is. All right, so the third section here is the rules that we're going to talk about, and makes it very easy to take derivative with these rules. So the first one is constant function. So what is the derivative of a constant function according to our definition? Well, according to our definition, if the function is f of x equals to c, and c is just a real number, there is no variable involved here, right? Just a constant. Then we have to do the same thing. What is f prime? Is limit of f of x plus h minus f of x over h. Now, f of x plus h, when the function is constant, is just c, right? It doesn't matter what the input is, right? This function is constant no matter what the input is always c, right? If you put a happy face here, you still get what? You still get c. So it doesn't matter what the input is, the output is c. Of course, happy face is not in the domain. That was just emphasizing the point that the input doesn't matter. Okay, so that would be c, and f of x itself is c over h, but c minus c is 0, so the derivative of a constant is 0. And we know, of course, it makes sense, because a constant means a horizontal line, and what's the slope of the tangent line to this curve? What is always horizontal? So that makes sense. So example, what's the derivative of f of x equals to 9? 0, because it's a constant, right? All right, what about the power? Well, the power rule says that if you have a function that has a power that is a positive integer, because when n equals to 0, we're going to assume that this is a constant, and we proved it already, right? So x to 0, we already proved that's just a constant. But if it is any integer, positive integer greater than 0, 1, 2, 3, whatever, then we can prove that the derivative of this would be just nxn minus 1, nx to the power of n minus 1. So the alternative notation would be d dx of x to the nth. Now we're going to gradually throughout this chapter, we're going to prove that you can actually use the same formula no matter what n is. So first we're going to prove it for n as a positive integer. Then we're going to prove that it could be even negative integer. Then we're going to prove that it could be a fraction. And then we're going to prove that it could be an irrational number too. like x to the power of the square root of 2. But this is, of course, coming at the end of this chapter. So right now we're going to prove it for an integer, positive integer. Also, don't get this confused by functions like this, where the base is a number and the exponent is a variable, right? Like that, or this one. If the exponent has a variable in it, that's a different story that we're going to talk about this one at the end of this chapter. For now, we're talking about power functions. Power functions are a variable to a number. But if you have a number to a power of a variable, that's a different story. It's an exponential function, and we're going to talk about them later. All right, so that is, let's do an example. What's the derivative of f of x equals to x to the 7th power? Well, it's 7 x to 6, right? So bring the n downstairs and then subtract 1 from n. That's it. What's the derivative of that? Well, that's what? That's a x to the 1st power. So we bring it downstairs and subtract 1 from 1 is 0. But this is what? This is 1, so the answer is 1. All right, so here's the proof. Now, this is from algebra or pre-calculus. It's the expansion of x to a plus b to the nth power. So the way you expand it is this right here. This notation of n and k is called number of combinations. So if you have, let's say, 3 letters, you want to take 2 letters out of 3 letters, how many different ways can you take 2 letters out of those 3 letters? Well, it looks like it's 3 different ways, right? Now, when we say combination, we mean the arrangement, the order doesn't matter. As long as I have A and B, I'm happy. I don't care whether I have B first and then A, or I have A first and then B. It doesn't matter. If the order doesn't matter, this becomes a combination. Another notation for this is combination n items taking k at a time. And it turns out that in expanding binomials like this, the coefficients of the terms of the expansion have to do with this idea of combinations. Okay, this you learn in algebra and pre-calculus. So I'm just going to tell you that taking n items n at a time, there is only one way to do that. And then this is defined to be 1. This is n, because you see, if I have like 3 different things, right? And I want to take them one at a time, how many different ways can I take them? Well, 3 times. So that's obvious, is n, right? And then n to n and n minus 1 is also n. The reason is that if I want to take, how many different ways can I take one of these? Well, 3 different ways. I could take A, I could take B, and I can take C. So that's 3 different ways, right? And this would be like, how many different ways can I take 2 items out of n? And it turns out to be the same, because taking 1 item is like not taking 2 items, right? So when I decide to pick A, at the same time, I'm deciding that I don't want to take these 2, right? So if you think of it that way, this is always the case, that n and k combination is always the same as n and n minus k. So number of choices that I have here to take k items is the same as number of choices that I have if I don't want to take k item. I want to take the rest of them. So that's the idea here. So you don't really, it is not that important. Now in calculus 2 is important to fully understand this and being able to actually expand it. But for now, we just look at this as basically polynomial with a bunch of terms. These are just coefficients, right? As I said, this n0 here, the first one is 1, and that's important to know. We want to know that this is actually 1, okay? The rest of them don't matter because they get canceled. So let's see. So what we want to do in order to find the derivative of x to n, we have to use this term, this limit, and in the limit we have this structure. So f of x plus h minus f of x over h. But f of x plus h would be that when you substitute x plus h for x, right? And f of x is itself. So f of x plus h minus f of x over h. So we have to simplify that. To simplify this, we need to understand how to expand this, right? Otherwise, we're not going to be able to do it. So we expand it. We're going to get this right here. Well, let me erase all that. So we're going to get this. That's the expansion. And now, if we subtract x to the nth power from this, what do we get? So let's write it down. Remember we said this is what? This is 1, right? And h to the 0 is 1. So 1 times x to n is x to n. So it looks like the first term here is only just x to the nth power. The rest of it doesn't matter because they get canceled. So we're going to take this, put it here, knowing that what? That this right here, this whole thing is just x to n. And then since you're subtracting at the end, we are subtracting x to n, they get what? They get canceled. So what we're left with is just the stuff in the middle here, right? So that's the numerator. Now the denominator, remember, is h, right? So you see, notice now that every one of these has an h in it, right? Before, in here, we had h to the 0th power, but we got rid of that, right? So we just start with h to the first and h to the second and so forth. So all of them have an h in them. So we're going to take that h out and then cancel that h with that h that we get out. And notice that when we get the h out, this one, the first term, is going to lose its h, but the rest of them retain at least one h, right? So the first term would be just x to n minus 1, right? Right? And n1. Remember, what is n1? n1 is n, right? So this would be n, right? And doesn't have h in it, and would be n times x to n minus 1. And the rest of these, since they have h in them, when h goes to 0, they get canceled. So the answer to this limit will be just what? That times x to n minus 1. Minus 0, which is just itself. And h is gone, right? So the answer is just that. So we prove that the derivative is what? Nx to n minus 1, if the power is what? A positive integer. And later we're going to prove the rest of them. We don't need all this algebra to prove the rest of it. But that's what it is. Again, if you don't know your expansion, you can just review it. It's in my pre-calculus videos. If you go to my channel and go to pre-calculus, you can find it. All right, so let f of x and g of x be differentiable functions and k be a constant. Then each of the following equations holds. So just like the limits, we have some rules we can use. Derivative of a sum is the sum of the derivatives. And if you have, of course, this works only if the derivatives of each function derivatives exist. If they exist, then derivative of a sum is the sum of derivatives, right? And the same is true for difference. The derivative of a difference of two functions is the difference of derivatives. And if we have a constant times a function, then the derivative of a constant times a function is the constant times derivative of the function. And here is a proof of one of them. They're easy to prove, but that's proof of the sum. So we assume that we have a function that is the sum of two other functions. So does h prime exist? Yes. If f of x has derivative and g of x has derivative, so does h. So let's prove that. So h prime would be the limit of h of x plus delta x minus h of x. Instead of h, I put delta x, but it doesn't really matter. So h of x plus delta h means, well, h is f of x plus g of x, so we just have to put it here. So this whole thing here, all this here, is h of x plus delta x minus h of x. But h of x is this whole thing, so we have to put it here. And then if you apply the minus here, distribute the minus, and put this f of x with f of x, and put g of x with the g of x, then we get actually two limits. And you see the limit is actually f prime plus g prime, right? Because we already know these are definitions of what? Of the derivatives of f and g, right? So put f of x with f of x and put g of x with the g of x in the numerator, rearrange them, and then separate them into two fractions with the same denominator. And that's what you have. The rest of them are proved similarly, so we're not going to worry about them. All right, so here is a derivative to do. What's the derivative of x to the 7th plus 10? Well, again, we apply the formula to x to the n. So we bring the 7 down and subtract 1 from 7. That's it. Plus, what's the derivative of a constant? 0. That's it. What's the derivative of 8x to the 4th plus 9x squared minus 1? Well, now we have a coefficient already. We keep the coefficient, right? So we keep the coefficient. And we say, okay, 4 comes to the front. That's another coefficient. And then 4 minus 3, 4 minus 1, which is 3, right? So that would be 32x to the 3rd. Plus, again, we keep the 9. Then we put the 2 before it or after, it doesn't matter. And x to 2 minus 1, which is what? 18x. Okay, here's another one. Now, we haven't talked about a quotient, so that's not a quotient. That's just the whole thing multiplied by 1/3, right? So we can put the 1/3 here, right? We keep the 1/3. And so this 1/3, think of this as 1 over 3, right? So we're going to take that, keep it here, and then take derivative of the rest of it. What's the derivative of x to the 3rd? 3x squared. What's the derivative of 2x squared? 4x. And what's the derivative of 4? 0. And then when you multiply by 1/3, that's what you get. Okay? All right. Is the derivative of a product the product of the derivatives? Remember with limits that was the case, but is it true for derivatives? Well, let's look at an example. Here is f of x, and here is g of x. Now, what's the derivative of f of x? It's 1, right? Because derivative of x is 1. Derivative of 1 is 0, so that's 1. What's the derivative of g of x? Is also 1. But what's the derivative? When you multiply the derivatives, you get 1. But if you take this function and multiply it by this function, right? That's the product. You're gonna get x squared minus 1. But what's the prime of the product? Is 2x, which is not the same as what we got here. So the answer to this is a big no, right? No. So derivative of a product is not the product of derivatives. But what is it? Well, let's see. The formula, I'll give you the formula first. If you have two functions, and if you don't carry these x's, it's easier to see what it is, right? So if I just put what is the derivative of f times g, like that, the formula is derivative of the first one times the second one, not the derivative of the second one, just the second function, plus the first function times the derivative of the second one, right here. That's the formula, very easy. We're going to prove it in a second, but that's all there is to it. You could also think of it as uv, u times v. U is a function, v is a function, and we are assuming all of them are functions of x. Then that would be u prime v plus u v prime. So it turns out that the rule for product of two functions, when you take derivative of it, is actually this, not the product of the derivatives. Okay? All right, so how do we prove it? It's a little algebra trick. So we're going to assume that h of x is f times g, and we are going to write the limit for it. So how do we find the derivative of h of x? What would be limit of h of x plus delta x minus h of x over delta x, right? And then we know h of x is f times g, so that's what we're going to get when you substitute, right, in this structure. I didn't put the limit here. We can simplify the structure first, and then we put the limit on it. All right, so what do we get? Well, look, you keep staring at this, and people have done that. People did that long time ago. They kept staring at it and worked on it, tried different ways, and they figured what they need is maybe the derivative, of course, derivative of h should be related to derivative of f and derivative of g. So if you look at this structure, can you make derivative of f and derivative of g out of it? Looks like it. So what we need here is the minus f of x, and what we need with this one is minus g of x, right? To make them derivatives of f and g. So that's what we're going to do. We're going to subtract f of x times g of x plus delta x and add to the numerator. That doesn't change anything because that is 0. Doesn't change the value of this. But what it does is this. Now we can put these together, right? We can keep the ones that have, this has f of x plus delta x in it, this one, right? And also, if you look at this one, right? This one has g of x plus delta x, and this one has g of x plus delta x. So if you take these two together, we can factor that g of x plus delta x from it, like I did here. And then, in parentheses, if you take that away from this expression, from this part here, you get f of x plus delta x. And if you take that away, you get f of x. And we got what we wanted. And then plus, then we're going to take these two and take f of x out of these two. Take f of x out. You take f of x out of here, you get g. Take f of x out of here, you get g. This is g of x plus delta x, and that's gx. So now we separate them into two, right? So what we have to do is, right here, we have the definition of derivative of f, right? And over here, we have the definition of derivative of, if we take that delta x with it, derivative of g. So this would be this times derivative of f, and this times derivative of g. And that's the proof, right? Because now we take the limit of it, and let delta x goes to 0. And we know this is derivative of f, and that is derivative of g. So that's the formula right there. We proved it. Okay? All right, so you can stop the video and take a look at this again and see if it makes sense to you. But I'm going to move on and do an example. So find h prime if h of x is given by this product. Okay, so h of x equals to, again, remember, h is f times g. So what's the derivative of f times g? Is f prime g plus fg prime. Is Important to write this first, not that, because when we talk about the quotient, we use the same structure again, but we put minus in between. So f prime g plus fg prime. That's all there is to it. So we write it. So what is f? That. So what's the prime of f? Is 1. And then g is that. So we just put it there. Plus f, what's that? That's x plus 2. And g prime, what's the derivative of g? Is 4x minus 0. So 4x right there. We're done. The rest of it is simplifying, and we get the derivative. All right, so that's the easiest thing you do in calculus. Taking derivatives, following a bunch of rules and steps is not really that much calculus anymore, because all of this is done by computers and calculators. So calculus is just application and understanding the concepts, right? Procedural stuff you need to know, of course. They expect you to know how to take derivative of a function, but it's not right. You have to be an expert in taking derivatives. Some of these become really tedious to take derivative of, but they're not difficult. They're just tedious. They're easy, but a lot of work involved, a lot of algebra. All right, so find h prime at 2. So first, this is h of x. So we are given that f at 2 is 3, f prime at 2 is negative 4, g of 2 is 1, and g prime of 2 is 6. Find h prime at 2. So we know that h prime here of x is going to be what? Is going to be f prime times g plus what? F times g prime, right? So that's the structure of it. Now, what is h prime at 2? Well, we just have to put 2 in all of these, right? So it would be f prime at 2 times g at 2, right? That's an f prime. Times g at 2, right? Plus f of 2 times g prime of 2. And this is messy, but I have it over here already, so let me erase this. So I have it down here already. So h prime at 2 would be f prime at 2 times g of 2 plus f of 2 times g prime of 2. And we are given all of those values, so we substitute and we have the answer, right? All right. Common mistake is to just multiply f prime and g prime. 6 times negative 4. That's not the answer, of course, right? All right, the quotient of two functions. The quotient of two functions has a formula too. So if you have a function that is f over g, and you want to take the prime of it, then the answer is f prime g, just like, you know, the product, but there is a minus in between. It is important to do f prime g first, because there is a minus. It does matter which one comes first. So you use the same structure, f prime g, f g prime, but a minus in between, and the denominator is g squared. The proof of this is similar to product. You have to basically use some algebraic manipulations and acrobatics, and you can get it. But for now, we're not going to worry about proof of the quotient rule. You can find it on internet. Just search for proof of quotient if you're curious about it. All right, so let's see. How do we do it? Well, that's it. We follow this formula. Very easy. So here is an example. We're going to think of this as f. I'm going to think of this as g, right? And it would be f prime g minus f g prime over g squared. So what is f prime? Well, that would be 1. What's g of x? It's this whole thing, so we put it there. Minus f of x, which is that. We put it there. And then g prime would be derivative of that. 2x minus 7 plus 0, right? So that's it. Denominator would be g to the second power. We are done. That's the end of calculus, beginning of the algebra. And you can simplify it here. okay? Just, do the operations. I'm not going to worry about that. You can do it on your own. You can stop the video and make sure this is correct. So that is the answer. That's the derivative of h. All right. If f of x equals to x to negative n, what is f prime? So that means, can we use this power rule if we have a negative number here? So can I say the derivative of this is the same as you just bring the negative 4 downstairs and then put negative 4 minus 1 in the exponent? And the answer is yes. And we can prove it. So all you have to do is write this as what? As 1 over x to n, and use quotient rule and treat this as, let's say u, and treat this as v, because we already use f here. So u over v. Now, what's the derivative of u over v? Is u prime v minus uv prime over v squared. So here, let u be 1, let v be x to the n, and then substitute in here and simplify it. And notice that, what do we get? Well, this would be 0, this goes away, so it would be negative n x to n minus 1 over x to n to the second is x to 2n. So we're going to end up with negative n as a coefficient, and this would be x to n minus 1 divided by x to 2n, which is x to n minus 1 minus 2n. And what is that? That's negative n minus 1, right? But notice it's the same structure, right? We started with x to negative n. Looks like we got negative n here. We brought it to the front, before it. And then we took negative n and subtracted 1, right? So that means, yes, this formula works for what? For negative exponents, right? Basically, x to whatever prime is what? Now whatever, whatever number. It would be that, and then x to that minus 1, right? So yes. So what we did right now, remember x to n, we proved that if n is 0, we're going to get just a constant, right? If n is 0, that's a constant. And if it's greater than 0, it's a positive integer, we proved it. And now is also true for negative integers. So far n could be any integer, and we can use this formula. All right. So what is the derivative of this? Well, we can think of this as x to the 4th, of course. And this one, don't think of it as quotient rule. Think of it as what? 2 times x to the negative 1, right? And it's easier to take the derivative this way. So what's the derivative of x to the 4th? We bring the 4 downstairs, subtract 1 from 4, plus, there's a 2 here, we keep it, and then negative 1 comes downstairs, and then negative 1 minus 1. That's it. The rest of it is simplifying, so that's the answer. And you can put that back in the denominator if you want. If you don't want negative powers, you can put it there. And that's the derivative. Here's another one. Don't think of this as product rule, because we can simplify it, right? Just first multiply, simplify, and then take the derivative, right? So x squared times 2 over x squared is just 2. And x squared times that would be, if we put the x squared here, so that would be x squared divided by x to the 3rd. So that's x to 2 minus 3, which is x to negative 1. So that's the 5, right? You keep the 5, and then x to negative 1. So that's the simplified function. Now we take the derivative. What's the derivative of that simplified function? Well, what's the derivative of 2? 0. What's the derivative of this? Keep the 5, bring the negative 1 downstairs, then negative 1 minus 1 is negative 2. Take it back in the denominator, that's it. So I didn't lie to you when I said taking derivative is really easy. So here's another one. What's k prime of x? If k of x is that. Well, you have to follow the formula. So what's k prime? Would be derivative of this, which we keep the 3 and take derivative of h, right? Plus. Now that's a product. So we think of this as one function, we think of that as another function. So let's call this like a f and g. This is g, right? So the answer to this part would be f prime g plus f g prime, right? So f prime g would be derivative of f, which is 2x, times g, right? Plus what? Plus f, which is x squared, times g prime, right? So that's the idea. And I have it over here so you can see it. So here we go. So 3h prime. This prime is right here, 2x times g plus g prime times what? Times x squared. And that's it. That's all we can do because we don't know what g of x is and we don't know what h of x is, so we're going to leave it like that. So that is k prime of x, right? All right. So what if you have 3 functions? What is the prime if you have the product of 3 functions? Well, we can think of these 2 as one function and times what? Times that. So if you do that, then the prime of this thing would be prime of this times that plus prime of this times this whole thing, right? So it's going to be like that. So it would be the prime of that, the first 2 times h, plus prime of h times those 2. And now, the prime of these 2 is a product itself, right? So we can do that now. The prime of these 2 would be f prime g plus g prime f. And the prime of h is just, it would be h prime. And then multiply by that, right? And then when you simplify it, you end up with what? The formula that is symmetric, kind of makes sense. Remember, if you have f and g by themselves, looks like you take derivative of the first one, multiply by the rest of them, plus then take the derivative of the second one, multiply by the rest of them. So for 3 functions, it looks like it is symmetric, right? So take the first derivative, multiply by the other 2, then take the second derivative, multiply by the other 2, and then take the third one, derivative of the third one, multiplied by the other 2, right? It's kind of symmetric. All right, so it works for 3 functions this way. All right, so let's do a few more of these. What's h prime? Now we are combining the quotient rule and the product rule. In order not to get confused, again, make sure you divide these into a bunch of functions, right? So for example, here you can think of this as a function, think of this as a function, and think of this as a function. Then follow the rules that we just talked about. So here we go. So derivative of numerator is a product, right? So the numerator would be derivative of, so if we have a numerator and denominator, let's think of this as, think of u over v, right? So that would be u prime v minus uv prime over v squared, right? So the denominator of our answer would be that v squared right here. Now, our u here itself is actually 2 functions. So our u is actually what? U is actually f times g. F times g, you can think of it as, well, f times k, since we already have k here. So when we set this up, u prime is actually a product itself, right? See that? So we're going to write it like that. So in the numerator here, let me do it here. So if I want to follow this, I'm going to have to write what? That h prime is going to be u prime v. Remember, u is the numerator, so it would be prime of the numerator, which is 2x to the third, and just put k. I don't put k of x, I just put k, right? So that would be u prime, right? So that's u prime. And then times v, which is 3x plus 2, minus, and that's the numerator, right? Oops. So that's my numerator. U v prime. U is this whole thing again, 2x to the third k times v prime. What's the derivative of v prime? Is 3. And divided by what? 3x plus 2 squared. Now, the numerator here is going to be derivative of this times this. I'm talking about just this one, right? So it would be derivative of this times this. What's the derivative of 2x to the third? 6x to the second, right? Times k plus derivative of k times this. So it would be 2x to the third k prime. And then we have to multiply that by 3x plus 2. And then minus, this is 6x to the third k over 3x plus 2 to the second, right? Now, we are done with calculus. This is a k prime here, right? That's a k prime. And the rest of this is simplifying it, right? So I'll let you do it this way. Stop the video and do this and make sure you get this answer. When you multiply everything, that's what you're going to get. Again, it's not hard. Some of these, they require some algebra, and you should work these out and make sure, reduce number of mistakes that you make by practicing. So stop the video and take a look at it and make sure you get that answer. All right, determine what a function has horizontal tangent. Now, when a function goes up and down, right? Now, horizontal tangent means that at that point when we draw the tangent, the line would be horizontal. So it looks like that one, like this one here, right? Or this one here, right? This one here. So how do we figure out where the function has horizontal tangent? And later this becomes important because in calculus, remember, we are interested in functions that increase and decrease, right? So it's important to know the top of the hills and bottom of the valleys, because those are the min and max values. We're going to call them relative min and max. But for now, how do we find them? Well, remember, that happens when f prime is 0, right? So if we are given the formula for the function, all we have to do to find the horizontal tangent line is to find f prime, right? We find f prime, and then set it equal to 0. So what's f prime here? 3x squared minus 2 times 7 is 14x to the first plus 8 times x is x goes away because 1 minus 1 is 0. So we get 8, and then the derivative of 1 is 0. So we don't put it there. Set this equal to 0, find the roots. You can factor or just use quadratic formula. The roots are 2/3 and 4. So, and this is the graph of this function. You see, right here at 2/3, right? What's that? That's 2/3 right there. It has a horizontal tangent line. And another one is at 4 right here. At 4, it has another one. Now, in algebra, you wouldn't be able to do this, right? How would you do this in algebra? How would you find the top of the hills and the bottom of the valleys? In algebra, we just learned how to do it with one of these, right? It was the vertex of a parabola either opening up or opening down, remember? And that has a formula. That had a formula like negative b over 2a and f of negative b over 2a. But that's the only one we could do in algebra. But now, you have a whole toolbox now. In algebra, you just had like a screwdriver or something. Now you have a whole toolbox. Now we can deal with any function and find those, but we're going to work a little bit more about this with this later on. Okay, so those are the horizontal tangents. Now more examples. Use the following figure to find the indicated derivative if it exists. So let h of x be f of x plus g of x. Find h prime at 4. Now notice that we don't have a formula to take derivative. We have to use this graph, right? So what is h prime of x? Well, that would be f prime of x plus what? G prime of x, whatever f and g are. And what is h prime at 4? Well, that would be f prime at 4 plus what? G prime at 4. Now, what's f prime at 4? Well, remember the definition, the interpretation of the derivative at 4 for f. Where is f? F is here. So we're going to go to 4 and see the tangent line, the slope of the tangent line at that point. Well, the slope of the tangent line here would be the slope of this line, actually. The curve is actually a line here. And is rise over run. So it's 2 over 2, which is 1. And plus, what is g prime at 4? Now, g is this one. At 4, well, g is horizontal at 4, so the slope of a tangent to it is also horizontal, which is 0. So the answer is 1 plus what? 1 plus 0, which is 1, right? All right, so you see, if you understand the concept, then you can answer this question. If you just know how to take derivatives, well, you get stuck here because there are no formulas to take derivative, right? All right, so I'm going to end this video, and we're going to let this be just section 3.3, and I'm going to do another video for the other parts of chapter 3, okay? So let me come back here and just say bye to you. See you next time in the next video. Take care of yourself and others.